general relativity step by step. Right, I'm going to identify the divergence of a vector field V written in my peculiar h theta coordinate system. You'll remember we've got a whole bunch of, so x equals h and y equals h tan theta, and we specified g, which was the determinant of the fundamental tensor, the metric tensor, which was h squared sec to the 4. Right, let's get going. We need to figure out v alpha comma alpha, and that's the total derivative. Sometimes you see it with a semicolon there, equals di v alpha by di x alpha, summed over alpha of course, plus Christoffel symbol alpha alpha beta v beta. And this term of course accounts for the fact that the basis vectors, the coordinate basis vectors, are not constant. I'm going to use my formula, well actually I'm going to write it out in its component form now. We've got di vh by di h plus di v theta by di theta, those two terms being this thing here, plus alpha alpha h v h plus, let me just write it down, alpha alpha theta v theta. These two terms here being an expansion of half, well, one of the two summations implicit in this term here, because it's summed over alpha and beta. I'm going to retain that one there because you remember I've got a formula for this. Yeah. So what is this? Let me just remind myself what the components of V are. Actually, I'll do that later. We'll come back to what that is later. Di VH by di H plus di V theta by di theta plus a half G minus 1 di G by di H, because it's there, VH, plus a half G minus 1 di G by di theta V theta. Equals. You see how intricate it is, and you've got to get absolutely everything right or it doesn't work. A half G to the minus 1. We know what everything is. Di G by di H V H. I'm just doing it one step at a time because it is so easy to make mistakes. Plus, we've taken out a factor of a half G minus 1. Di G di theta V superscript theta. Now I'll just remind myself what VH and V theta are. VH was just equal to alpha, and V superscript theta was equal to minus alpha H minus 1 sine theta cos theta plus beta H minus 1 cos squared. So you can see we've got a fairly difficult job to do. So that equals di VH, di alpha by di H, which is of course equal to 0, so I'm going to cancel that out straight away. 0, there you go, doesn't that feel good? Back to black. Plus di by di theta of minus alpha H minus 1 sine theta cos theta plus beta H minus 1 cos squared theta. Is that right? Yeah. That's that term there. I ought to, maybe I'll connect them in a different colour. Let's try green. That goes there. This term is this one here. That term there. I'm going to have to cross over myself, aren't I? Back to black. Plus a half. The determinant of the metric tensor was h squared sec to the 4th theta, but it's 1 over that, so it's to the power minus 1. Times di G di H is di by di H of h squared sec to the 4 theta times VH. What was VH? Alpha. Plus, that's that term. Maybe I should draw it in green anyway, maybe with a dotted line. Green. This term here is that term there. There we go. Back to black. This term here now, di by di theta of h squared sec to the 4th theta times, I'm going to put that in brackets because it's easy to think the differential continues to the whole thing, v superscript theta, which is this thing here, times minus alpha h minus 1 sine theta cos theta plus beta h minus 1 cos squared theta. Close. What else have I got to close? I've got to close this one here. These terms here, I'll do it in green. Green. These terms here, that one and this one, I guess, they are this term here. So I'll just go, that's there. Alright, so have we got everything? I think we have. I think we've got everything there. We've got the two direct differentials here. Okay, now remember it's a constant field because we had alpha in the x direction and beta in the y direction, but those components change, and they're changing with respect to a coordinate basis system which is itself changing with space. Alright, let's do some more multiplication. What colour am I on? Oh, I'm still on green. Black. Right. So, I'm going to say it's minus alpha h minus 1 for this bit here, times the differential of sine times cos is cos squared theta minus sine squared theta. I'll do the betas later. I'll just do the alpha terms. Just the alpha terms. The alpha terms. I'll do the betas later if I can. I'm not sure I'm going to get this right. That's closing brackets there. Let me just... That is this term here, but just the alpha terms. I'm not doing anything else. I'll do the beta terms later. Plus 1/2 h minus 2 cos to the 4th theta, which is this term here. That's there. That's that term there. So easy to make a mistake. There's so much to go wrong here. I did this about a dozen times. Multiplied by a whole bunch of stuff. This term here is 2h sec to the 4 theta times alpha, but I'm only looking at the alpha term. I might as well write it in. Times alpha, which is this one, plus this term here, di by di theta. So the h squared comes out. Differentiate sec to the power 4. We have got 4 sec cubed theta times differential of sec is sine theta sec squared. That's that term there. Put that in brackets. Times, and I'm just doing the alpha term here. That term is this term here. Now we've got minus alpha h minus 1 sine theta cos theta equals alpha h minus 1 times sine squared theta minus cos squared theta, which is that term, those two terms there. Easy to forget those. That one's that one, and this one's this one. Back to black. Plus, you see the powers of h are all h minus 1, and I've got the h minus 1 here, and I'm only looking at the alpha terms here. So, what have I got? I've got a cos to the 4 times sec to the 4, and that's a 2 and that's a half, so that's just a 1. That's that term there. I'm going to tick that one off in red. Done. And I've done those two as well. There you go. Back to black. Plus 2. Why is it 2? It's because I've got a half there and a 2 there. The h has gone. The h has been factored out. We've got a cos to the 4. I'll write it all in. Cos to the 4 theta from there times sec to the 5 theta. What have I got there? Sec to the 5 thetas from where? It is from there and there, giving me 2 factors of sec, 2 components there. What have I got left? I've got sine squared times a cos. Sine squared theta, which is that one and that one, times a cosine theta. Now I've got a plus here, and I think it's a minus. Yes, it's a minus. Minus. Have I got a bracket to deal with? Yeah, I guess I should put the bracket in. There it is. Equals alpha h minus 1 sine squared theta minus cos squared theta plus 1 minus 2. Oops. Does that from time to time. Minus 2. What have I got here? I've got a factor of sec and a factor of cos. So they cancel out. Sine squared theta equals alpha h minus 1 minus cos squared theta minus sine squared theta equals 0. QED. That's a bit tense. The reason it's tense is that I've done this a dozen times and I've got it wrong each time. There is so much to remember. But let me just impress upon you again how much time this formula here saves. You'll remember I got myself all tangled up in knots because I was trying to evaluate the Christoffel symbols. And you're going to need all 4 of them if you want to do it the full way. And here, it's a lot easier because I'm only considering the the determinant of the fundamental. The determinant of the metric tensor. And we know that the coefficient is 0. Let's have a look at see what we need to do for the betas. Maybe I'll come back and do the betas. I'll do it in a separate screencast. I'm going to stop there because I don't want to screw it up. So I'm going to stop there. Stop.